There is a certain light that settles in old laboratories, the steady, cool glow of instruments, the smell of chemicals like a memory, the faint electric hum that keeps the hours measured. In that light, things are revealed not all at once, but line by line, layer by layer. The grain of film, the shadow of a rod of glass, the pattern left by invisible rays. It is under that light that a woman with an uncompromising attention to detail learned to read the hidden architecture of matter. Rosalind Franklin arrived at her work like someone trained to listen. Born in London in 1920, she came of age in an era when the world expected few of its women to work at the edges of knowledge. She trained in chemistry and found her true craft in X-ray diffraction, a method that makes the invisible visible by turning a crystalline sample into a pattern of light and dark, a language of spots and symmetries. She learned to translate those patterns into form and proportion. Before the word DNA carried its haunting promise, she had already become a master of the glass and the film, of dark rooms and long exposures, of coaxing order out of dust and shadow. The work she did in the 1940s and early 1950s was practical and exacting. She examined coal, then moved to more refined structures in Paris, then returned to London to look at the molecular threads that carry life itself. At King's College, she studied threads of DNA in their natural hydrated state and in a dehydrated form, recording differences in pattern with a patience that bordered on the austere. Her notebooks were dense with measurements. Her notebooks were, in a way, her voice, terse, precise, refusing speculation without data. What she produced in that room was both simple and decisive. An X-ray diffraction photograph, a rectangle of silver halide film flecked with a geometry that, to the practiced eye, was unmistakable. The image, later known as Photo 51, captures a pattern like an X carved into a night sky, a cross of light with repeating arcs, bright spots arranged with an order that suggested repetition and fit. For the scientist who had trained herself to read such patterns, it spoke of a helix. It spoke of regular spacing between components. It gave measurements, a distance between repeating elements, the pitch of the coil, the radius of the turn. Those numbers, small and exact, the spacing of base units by a few angstroms, the rise per turn measured in tens of angstroms, were the scaffolding on which a structural model could be built. She had been cautious in her conclusions. She distinguished between two forms of DNA, A and B, and she dissected how hydration changed the structure. She warned against hasty models that ignored the data. Her empiricism was rigorous, uncompromising. She wanted multiple angles, more exposure, better statistics. Yet the photographs she made and the calculations she published became the missing piece someone else would use with impatient joy. At Cambridge, in a room filled with cardboard models and cardboard certainty, two other young scientists were racing to assemble a model of the molecule of life. They had insights and intuition. They had theoretical appetite. What they also needed were the numbers that would let the model lock into place. Science is often a social enterprise, as well as an intellectual one. And in those years, the corridors between laboratories were quick with exchange and at times with secrecy. Data moved. A report left a library table. A photograph changed hands without a permission form. The image that would so clearly point to a double helix reached those constructing the model, and they used it. The result was a structure elegant and complete. Once it existed in space, it seemed inevitable, like a truth waiting to be recognized. It was published in 1953, and the world changed as words like double helix entered public imagination. But the story of how the model was put together is not the same as the story of how credit was assigned. Rosalind Franklin continued her work with the same meticulous rigor that had guided her to the photograph. She moved to another laboratory and turned her attention to the viruses that would occupy the rest of her short career. Yet the currency of a discovery is not always the same as the currency of history. When prizes were given and narratives written, the weave of collaboration, competition, and casual negligence left her name in the margins. A Nobel Prize followed in 1962 for those who had been celebrated as the discoverers of DNA's structure. By then, she had been gone 4 years. She died in 1958 at 37 from ovarian cancer. Her death closed the book on a life of rigorous inquiry, but it did not close the questions her work raised about who is allowed to be credited, whose images become icons, and how the narrative of discovery flattens the complex human pathways that lead to insight. The photograph, that crystalline cross in a darkened room, became famous. She did not. For years, the story told itself in ways that made certain names larger and other names small. Her reputation was complicated further by portrayals that reduced her to an awkward caricature, rather than acknowledging the focused scientist she was. Resolute, private, exacting. Qualities that, in an institution unaccustomed to women in authority, could be misread as abrasiveness. In the quiet after the fever of the discovery, however, the evidence remained. Her data, her measurements, her insistence on multiple forms of DNA, these were not opinions to be erased. As scholars revisited the archive, as colleagues reflected, as the younger generation of scientists looked back, a clearer picture emerged, that the double helix could not have been proposed in its precise mathematical detail without the empirical backbone she provided. Her techniques mattered, her image mattered. The moral contours of how that image was used, without explicit permission, in a climate that often dismissed women's contributions, matter too. Her later work on the structure of viruses was no less important. At a different college, she mapped the molecular geometry of tobacco mosaic virus and polio. She published papers, trained students, and continued to demonstrate a powerful combination of experimental skill and analytic restraint. Her notebooks remained an artifact of a mind that trusted the quality of data over the glamour of proclamation. And yet, even as her professional reputation regained some balance in the following decades, history's ledger retained stains. Scientific recognition is not simply a ledger of facts. It is also a record of human choices about acknowledgement and voice. The story of Rosalind Franklin has become for many a mirror. It reflects the ways institutions can obscure contributions, the ways gender and temperament can shape a legacy, and the small cruelties that emerge when ambition meets the social architecture of scientific life. It also reveals how persistent evidence is. Photographs do not lie. They can be misused, misfiled, misattributed, but they remain as witnesses. When later generations looked back, when historians dug into notebooks and correspondence, they found the scaffolding that supported that famous model, a pattern of X's and spots and arcs, the repeating geometry of life rendered in silver on film. Recognition, belated as it sometimes is, reshapes not the past, but our understanding of it. Today, her name appears on halls and institutes, on plaques and lectures. Students read her methods, scientists cite her work. The photograph she made, the one that looks in its starkness like a fragment of some cosmic cipher, hangs in museums and in textbooks, a stark reminder that discovery is rarely a solo act, that the path to understanding is built from patient observation as much as from theoretical daring, that the tools of science, the camera, the darkroom, the meticulous annotation, are as central as the flash of insight that fashions a model. There is something elegiac about the way time tends to reassign credit, to scrub certain hands from the narrative and then, slowly, to add them back. The arc of Rosalind Franklin's story compels us to ask not only who discovered what, but how we tell those stories, who gets to speak them, and what we owe to the contours of truth itself. Her life was not an appendix to a greater tale. It was a vital chapter. The image she made continues to bear witness, precise, beautiful, implacable. When you look at that photograph now, it is easy to romanticize the moment, the flash of insight, the final placement of a piece in a puzzle. But the deeper truth is quieter and more human. It is the hours alone in a lab at midnight, the steady hand that adjusts the film, the scientist who refuses to draw conclusions from partial evidence, the person who insists that a measurement, however small, must be right. It is also the reminder that how we share data, how we credit labor, how we compose our histories, shapes the future as surely as any experiment. She did not live to see the full extension of the revolution her work made possible, the mapping of genomes, the medical breakthroughs that would follow from an understanding of DNA's architecture. But in laboratories around the world, in the cautious hands of students learning to read diffraction patterns, in the institutional debates about fairness and recognition, her presence is felt. The photograph remains like a small, stubborn lighthouse in the archive, guiding us back to a simple fact, that the structure of life was revealed in part by a woman who asked for nothing more than clarity. So we return to the light in the old laboratories and listen to what the film still tells us. The pattern is clear. The small, exact numbers spell out a shape, and behind the image is a life devoted to making sure that science is, above all else, true to what it can show us. In the end, the double helix is not only a symbol of biology, but a reminder that recognition and justice are part of the architecture of knowledge, and that a single photograph can change the world if one is willing to read it.